You've seen this number or this word already in this chapter. In fact, it was part of the title of chapter 6, decimals, colon, rational and irrational numbers. We're now going to talk about what rational numbers are, give it a definition. We're going to talk about repeating decimals and terminating decimals, and how to write them actually as these things called rational numbers. We're going to end this particular video with, I think it's a fun little mathematical trick. It will be probably one of the more challenging things that we do in this section, though. So up until now, when you've seen numbers written like this, we've called those things fractions, right? That's our common terminology for things that look like this. However, the word fraction is a bit of a generic term, and we are going to now be digging in a little bit more and using this definition for what we call rational numbers. A rational number is any number that can be written in the form a over b, where b is not equal to 0, and a and b are integers. It's called a rational number. And so it's still of the form a over b. It looks like a fraction, but notice how this definition says any number that can be written as a over b. It doesn't say it is written as a over b. It says it can be written as a over b. So there are lots of different types of numbers. Not all of them look like fractions, but many of them can be written as fractions with a little manipulation. So that's what we're going to spend our time doing. It is important to note that b cannot equal 0 because you can never have a 0 in the denominator of a fraction. So let's examine rational numbers a little bit more. Sometimes it's fairly easy to see that a number is a rational number because it looks like this. 1/9, 1 over 9 is written a over b. It's written as two integers, 1 and 9, in that form. We could have -3 over 7. Remember, an integer can also be negative. So -3 over 7 is also a rational number. Now, what about a number like this? Is that a rational number? Remember, the definition says it's a number that can be written as the form a over b. So the number 6 can be written as 6 over 1. Any whole number can be written over 1. And then it looks like a fraction. Then it is a rational number. So the number 6 is a rational number because it can be written as the fraction 6 over 1. So integers are also rational numbers. Now, rational numbers can be expressed using many different numbers or similar symbols or numerals. Think about this. That's a rational number that looks like a fraction, but we've seen that also represented as this in this particular chapter, 0.3, 3/10. So a decimal number like 0.3 is also a rational number because 0.3 can be written as 3/10. Remember, it all goes back to, can it be written as a fraction? So decimals can be fractions as well. We're going to find out that some decimals can, but not all decimals. So let's examine some of those. So this is a decimal number, 0.64, that we would say as 64 hundredths. So it could be written as 64 over 100, which is a fraction, so it is a rational number. Even if we put a whole number out front, 7.283, could that be written as a fraction? Absolutely. We still use the same numbers that were in the original number, 7,2,8,3. We just put the whole thing over whatever that last place value is. It's the thousandths place. So over 1,000. Notice that this is what we call an improper fraction, where the numerator is greater than the denominator. That's okay. It's like that because we had a whole number out front. Improper fractions have a value greater than 1. Now, sometimes we look at a fraction like 1/4. Let's go the other way now. And uh, we're talking about like going back and forth between fractions and decimals. We were kind of going one way here. Let's go the other way now. I do want to investigate how you could take a fraction and write it as a decimal number. One way is through division, but we're going to take it from a slightly different approach right now. Sometimes you have to ask yourself, is there a way using manipulation of fractions that I could take whatever denominator I was given and rewrite it as some power of 10? Could I take 4, multiply it by something, and turn it into 10 or 100 or 1,000 or something like that? And if you think about that, what you might find is that if you multiply 4 by the number 25, it gives you 100. And so the numerator would also get multiplied by 25, and we get 25 over 100, which is 0.25. So that's a convenient way for us to look at a rational number like 1/4 and change it into a decimal number like 0.25 or 25 hundredths. Now, these are all examples of what we call terminating decimals. Terminating decimals. To terminate something means to end it. And all of these decimal numbers came to an end. 0.64, that was the last number we wrote. 7.283, it's done. This fraction, 1/4, it ended right there after 0.25. And so again, that's what we call a terminating decimal. So we're going to explore this idea of terminating decimals for a moment here. Specifically, we're going to look at some fractions or rational numbers, and we're going to determine, can this be written as a terminating decimal? If I write this as a decimal, is it going to end? Now, you can certainly do this in a calculator through division, but we're taking a more in-depth analytical approach to this, as you can see. So I'm going to look at the number 3/8, 3/8. And I'm going to take you back to chapter 5, I believe, where we talked about what was called the fundamental theorem of arithmetic. It might have been chapter 4, but it had to do with prime factorizations. And we're going to look at this denominator, 8. And do you recall what the prime factorization of 8 is? A factor tree might help you get there. 2 and 4, 2 and 2. We've got a bunch of 2's. So 3/8 is the same as 3/2 to the 3rd power. Okay? Now, let's think about what I mentioned earlier. We're just going to save this. I'm going to put this on hold for a moment. When I was playing around with the number 1/4, I asked you the question, was there a way to take 1/4 and turn it into some power of 10, right? I said, can we take a 4 and turn it into a power of 10? Because once we do that, then we're in a form that allows us to write it as a decimal, because those powers of 10 are going to be our place values. So if we look at 3/8 and we did its prime factorization, we've got 3/2 to the 3rd. Let's think about those powers of 10 for a second, and what their factorization looks like. The number 10 is equal to 2 times 5. Agreed? What if we do 100? If you do a factor tree for this, I'm not going to show the whole thing, but if you do a factor tree and list out the prime factorization, you'll see it looks like this. 2 to the second times 5 to the second. And then if I say, what about 1,000? Again, we're thinking about this denominator here. 10, 100, 1,000. If you do a factor tree, you'll find the prime factorization is 2 to the third times 5 to the third. And that pattern continues. So, is there a way that we could take 3/8 and write it as a fraction with a denominator that's a power of 10? Notice what we have right here. I can grab my highlighter. Notice this last one right here. 1,000 is equal to 2 to the third times 5 to the third. We have a 2 to the third because of that 8. What happens if we multiply by 5 to the third on the top and bottom of that fraction? We have the same number of 2's that we do 5's, and when we multiply those together, they're going to equal 1,000. On the top, once we multiply that out, 5 to the third is 125, and 3 times 125 is 375. This can now be written as a decimal number. 0.375, 375 thousandths. So why did I walk you through this whole process? Because this seems like a lot. Well, we're going to find out in a minute. It really has to do with, can we write a decimal number or a fraction as a terminating decimal number? And the answer to that will always be yes, if our denominator can be turned into one of these types of numbers, a power of 10. And so we're going to explore some situations where we can do that. And then we'll look at situations where we can't do that. And we'll look at, like, what's the difference between them? And so I'm going to start with this. 7 over 20. I can find my decimal. We're going to take 7 over 20. And the question is, can we write this as a decimal number using the ideas that we just played around with? Remember, it's all about, can we turn it into a power of 10 in the denominator? So go ahead and pause and think about that. And what you may have come up with is, if we take 20 and multiply it by 5, we get 100. 7 times 5 is 35. We now have 35 over 100, which is 0.35 or 35 hundredths. So 7/20ths can be converted to a fraction with the denominator that's a power of 10, and then we can write it as its decimal version. How about this? 3 over 25. Similarly, we can take the denominator, 25, and multiply it by 4. And just like in the previous problem, that gives us a denominator of 100, and then a numerator this time of 12, which can be written as 0.12 or 12 hundredths. Now, not all of them are that easy. Not that those are easy, but I think that most of us could probably use what we call inspection. You could look at these numbers and say, I know how to change those into 100, maybe with a little playing around. But this one's a little bit harder. 11 over 16. And so this might take what we did earlier on this problem with the 3/8. If you can't immediately tell how to change the denominator into a power of 10, then you might want to try factoring it. If we factor the number 16, you will find through that process that it's equal to 2 to the 4th. If you want to try it out, do your factor tree bars, and you will find that it's 2 times 2 times 2 times 2. So do you remember what we might do here if we want to change this into a power of 10? we have to have an equal number of 2s and 5s. Recall from this example right here. For every 2, there's going to be a 5 that balances it out to create a 10. Because we have 4 2s in our denominator, we're going to have to multiply this by 4 5s. 2 to the 4th times 5 to the 4th will be a 1 with 4 zeros. Just like when I scroll back up here, 10 had 1 of each, 100 had 2 of each, 1,000 had 3 of each, and so 10,000 will have 4 of each. And then we would have to multiply 11 times 5 to the 4th. It gives us a fairly big number, 6, 8, 7, 5, once we multiply it all out. But then we have 6,875 10,000s, which as a decimal is written as 0.6875. So again, that's a little bit harder, but it's all about matching up 2s and 5s. Here's one more. Take a moment and see if you can figure this one the same way. If you start with your factor tree, you'll see that this is going to be 3 over 40, which is 2 to the 3rd times 5. 8 times 5 is 2 to the 3rd times 5. So did you figure out what to do with this one? Well, we already have 1 5 and 3 2s. We need an equal number of 2s and 5s. So if we multiply this by 2 more 5s on top and bottom, then we'll have 3 5s on bottom, 3 2s on bottom, which will give us 1,000, remember 3 zeros. And then on the top, we will have 75. 3 times 25 is 75. As a decimal, then, that is 0.075, 75 thousandths. So what this really comes down to is we are examining terminating decimals. Remember, decimals that come to an end. You will always be able to write a number with terminating decimals if and only if the denominator has only 2s and 5s in its prime factorizations. This is, again, a sort of formalized definition. So again, if a non-zero rational number, a over b, is in its simplest form, notice all of these that I gave you were completely reduced, it can be written as a terminating decimal. Remember, it's going to end if and only if b, the denominator, has only 2s and or 5s in its prime factorization. It can't have any other numbers as part of its prime factorization, only 2s and 5s, because those are the ingredients, the prime factors in every single power of 10. So what does that mean for us then? It means that there are some numbers that we can't write as a terminating decimal. So let's look at some examples. And the question here is, are we able to write this as a terminating decimal or not? And if so, then let's try it. So how about the fraction 5 over 6? If we explore that denominator and look at its prime factorization, we'll see that 6 is equal to 2 times 3. So just by looking at the denominator and seeing that it's 2 times 3, it's got a different number other than 2 and 5 in the denominator, which means no, it cannot be written as a terminating decimal. When we write this as a decimal, it's going to be called what is a repeating decimal. The decimal number is going to go on forever. We'll examine more of those in a moment. Now let's look at 1 over 80. Will this be able to be written as a terminating decimal? Well, we have to start with the factorization. So if you haven't paused and tried that yet, go ahead and do that. 1 over 80 can be written as 2 to the 4th times 5. 2 to the 4th times 5. Notice how the prime factorization has only 2's and 5's. It has 4 2's and 1 5. So if we wanted to write this as a decimal, we would need 3 more 5's. So we would multiply by 5 to the 3rd, by 5 to the 3rd. Together, there are a total of 4 5's in that denominator. And so our new fraction would look like this. 4 zeros, so 10,000. Our numerator would be 125, and we would have 0.0125. 125 in that 10,000ths place. So again, the first one had a 3, so it cannot be written as a terminating decimal. The second one only had 2's and 5's, and so it was able to be written in its terminating form. So here's one more. We haven't seen one quite like this yet. 9 over 15. Play around with this for a moment and see if you can figure out, can it be written as a terminating decimal? Now you might have started this problem by doing the prime factorizations. Said 15 is equal to 3 times 5. And maybe right there you stopped and said, oh, well, there's a 3 in there, so it's not able to be written as terminating. But if you look at the numerator 9, that could be factored into 3 times 3, and we have a common factor in the numerator and denominator. And those can be canceled out, leaving us with a simpler version of our fraction, 3 over 5. And then our denominator only has 5's in it. So to get it as in its decimal form, all we need to do is multiply the top and bottom by 2. That gives us the fraction of 6 over 10, which would be 0.6 or 6/10. So you do have to make sure that it is in its simplest form. So let's take a little bit harder look at these repeating decimals. And we'll start by examining what's maybe the most common repeating decimal, 1/3. You might even know this one. What I'm going to do is show you a little visual of why it repeats. And then we'll look at some long division to see what that actually looks like in practice. So we know that from the fraction quotient concept, something we discussed back in chapter 5, section 5.2, that 1/3 is equal to 1 divided by 3. A fraction can mean the same thing as that division. And so let's look at a decimal square that shows what that looks like. So imagine taking our decimal square and cutting it up into 10 equal sections. And then we're going to divide that by 3, right? So we're going to see, right, dividing 10 tenths by 3. We're really looking at it like that, 10 tenths. And we go into 3 equal sections. We have 0.3 here, 0.3 here, 0.3 here, and we've got this left over, right? We've got 0.1 remaining, okay? So this probably looks familiar to you from when we were working with fractions in a previous chapter. So we start with that, okay? So we've got 3 sections there. And now we're going to try this piece right there. And on the next visual, we're going to cut that thing into 3 pieces. So I'm going to move you and take this. I'm going to move it over here. And then what I'm going to do is I'm going to show what happens with that section over there on the end. And let's shrink you so you're the same size, because I think it's a little easier to make sense of it when they are identical. Okay. So if we take this 1/10 that's remaining over here on the right, and we just look at that, right? We're just going to pull that one off to the right. And then we're going to take this, cut it up into 10 equal pieces. Now we have hundredths. And we're going to segment that off into 3 equal groups. So here's one, and here's one. We have 0.03, 3 hundredths. We've got another 3 hundredths, and we have another 3 hundredths. What do we have left over then? Would be considered that remainder. Well, we have 1 single hundredth left right there. Well, now imagine doing that exact same thing again. Taking this little square, putting it here, cutting that up into 10 pieces. Now each of those are representing thousandths. Let's segment them into 3 equal sections, each one of them being 0.003, kind of like here, and then there's going to be 1,000th remaining. This is just going to keep on going, no matter how small we make this extra little section, right? The extra section here was that. Then it was this. Then it's this tiny little piece right there. And so what we end up with is 1 divided by 3 equals 0.3 from here, another 3 in the hundredths place from here, another 3 in the thousandths place from here, and it just keeps going, right? That's going to go on and on and on forever. That is a repeating decimal, or we may even call it an infinite decimal. Now, this whole big visual process that you can see is also connected to the division algorithm. We're going to do more with the division algorithm in a future section in this chapter, but we have seen this in earlier in the course. And so what we're going to do is we're going to take 1/3, we're going to represent it as 1 divided by 3, and then we're going to do the division algorithm. So it looks like this, 1 divided by 3. Now, the way that we approach this is we write our decimal point after the 1, and we put a 0 here. Because we think about 3 dividing into 1, which it can't do, but it can divide into 10 tenths. And it goes 3 tenths of a time. And so 3 times 3 is 9, and then we subtract. And so again, 3 goes into 10 3 times, but we're using our decimal point right above where we started. And then we multiply 3 times 3 to get 9, which we'll subtract, and that leaves us with 1. Because we have a remainder, this remainder is 1/10 because of its positioning, okay? We will then put another 0 here in the hundredths place. We will drop it down. 3 divides into 10 3 times. Really, this is 1/10 or 10 hundredths. And so it goes in 3 times. 3 goes into there 3 times. But we usually just think about this as the number 10 itself. But then we multiply again. 3 times 3 is 9. Subtract, and we get 1 again. We put another 0 in the 10 thousandths place. Drop the 0 down. 3 divides into 10 3 times. And so you can see what's happening here. It's just going to continue on and on forever. There's never a way that we're going to get a terminating decimal, right? It's going to repeat forever. And so we continue it. The way that we often show that numerically with some sort of symbol is saying that 1/3 is equal to 0.3, and then whatever part of our answer is repeating, we put a line over. Okay, this number that repeats is called the repetend. So that's how we can write that. Now, I think it is nice to show in comparison to the one we just did, one that we looked at earlier, which was 3/8. If we think about that as 3 divided by 8, we would do long division that looks like this. So this is for just a comparison purpose. If we treat this as 3.0, 8 divides into 30, 30 tenths, 3 times. 3 times 8 is 24. When we subtract, we get a remainder of 6. Add a 0 to that hundredths place. Drop that down. Now we're working with 60 hundredths, but we're just going to treat it as 60. 8 divides into 60 7 times. 7 times 8 is 56. When we subtract, we get a 4. Add a 0 to that thousandths place. Drop it down. Now we have 40. Really, it's 40 thousandths. And 8 divides into that 5 times. And you'll notice here we have a remainder of 0. So sometimes we are able to get a nice, neat terminating decimal when we do long division. Sometimes we are not. And so you can see the difference there between those two different situations. Now, the 1/3 example, we had 0.3, 3 tenths, and that 3 repeated. It was a single digit that repeated. Maybe what I'll do is have you even try this one. 4/7. Consider this 4 divided by 7. And when you set up your long division, the number you're dividing by, the divisor, always is on the outside of our division sign. And so we would set this up as 4, and we'll have to start with a 0.0, and our decimal point will start up there on that line. So see if you can do a little long division, work through this, and see what happens, okay? If you've tried this, I'm not going to work through the whole thing, but I'm just going to do a little demonstration or show you of what it should look like when you are done. And so 4 divided by 7, 7 goes into 40 5 times. Subtract the 35 to get 5, bring down the 0. Now it's 50. 7 goes into 50 7 times. Subtract the 49, you get 1, bring down the next 0, etc. And what you end up with here is 0.571428. And then all of a sudden, we get a 5, and we get another 5, right? It's the second time that we've seen a 5 in this string. And what's going to happen now is if we multiply 5 by 7 and get 35, and subtract, we get a 5, bring down another 0, we get 50, 7 goes into 50 7 times. Well, we've already seen that play out, right? We already saw 7 times 7 is 49. We already saw that right here, 35, 50, 49, 35, 50, 49. This whole part of the process will just repeat itself again, and we will get 5, 7, 1, 4, 2, 8. 5, 7, 1, 4, 2, 8. So in this case, we ended up with 0.571428, and then that would repeat. So we put our line over the entire grouping of the numbers that repeated. Okay, and you can see them again here, 5, 7, these remainders, right? Now, I think it is also important to note that when we ended up with 6 different repeating digits there, right? And so it can be more than one. As I mentioned before, this number is called that repetem, the part of the number that repeats. And so if we go back to the idea of rational numbers, every rational number is going to be able to be represented by either a repeating decimal or a terminating decimal. It's going to be one or the other. And so let's do a little practice of this, because this does take a little practice. So the first one we'll do is 3 over 11. And the second one that we will do is 5 over 12. So take a moment, do the division, see if you can do the long division on these, and figure out what this is going to look like as a decimal, When we do 3/11ths, we're going to divide 3 by 11. We'll put our 0 in there, and then we'll start the process. 2 times 11 is 22. We subtract, we get 8. 11 goes into 80 7 times. 7 times 11 is 77. Subtract, and we get 3. And right there, we hit the spot where we are going to be able to stop. Why? Because we already had a 3. If we go through the process again, we're doing 11 into 30, and we've already done that. We know it goes twice. So this is the part that repeats. We can say that 3/11ths is 0.27 repeating, 27 hundredths repeating. 5/12ths is a little bit different. 5 divided by 12. I'll write it as 5.0. 4 times 12 is 48. Subtract to get 2. Add another 0 and bring it down. 12 goes into 20 once. 1 times 12 is 12. Subtract to get 8. Add another 0 and drop it down. 12 goes into 80 6 times, which is 72. Subtract u to get 8. Ooh, we just had an 8 in our last step. If I add another 0 and drop it down, 12 goes into 80 6 times again. There's our repeating digit. So what do you do here? The 4 and the 1 are not going to repeat. It doesn't start repeating until it gets to the 6. So we say that 5/12ths is 0.41, and the 6 gets the repeating bar. 6 is the repetend. You can have part of your decimal not repeat, and the other part does. So this one doesn't actually start repeating until it gets to the thousandths digit. So every rational number is the quotient or the ratio of two integers, and we've seen them be repeating or terminating, right? They can be either one. If we flip that around, say conversely, every terminating or repeating decimal can be written as the quotient of two integers. And if you remember, what was the definition of a rational number? A rational number is a number that can be written as the quotient of two integers. It can be written as a fraction. So every terminating or repeating decimal can be written as a fraction. The terminating ones are fairly straightforward. 0.378. How can we write that as a fraction? Well, the easiest way is to take 378 and just put it over whatever that last place value was. 1,000. There you go. You're done. That's it. 0.47. You can also just say, how do I say this number? 47 over, what's that last place value? 100. 47 hundredths. Again, even a mixed decimal, like 64.3, can be written as 643 over, what's that place value? 10. So the terminating decimals, fairly straightforward to write them as a rational number, looking like a fraction. What gets challenging is when we have our infinite repeating decimals. How do we write those as a fraction? This is going to be one of the more challenging things we do, but I think it's kind of fun. So I'm going to walk you through this process. And the first few, I think you'll be okay with. Once we get to maybe the third or fourth example, there's some nuance that we have to pay attention to. We're also going to use a little bit of algebraic manipulation. We'll see algebra more later in the course, but we're going to use some basics of algebra as we go through this. So we're going to say the decimal 0.37 repeating. And again, we want to write this as a fraction, a over b. I want it to be able to write it as a ratio of A over B. So we're going to start by saying, let's let n equal 0.37 repeating. We're using n as a variable to represent this specific number. We know it also is equal to 0.373737, etc. So we're defining what our variable is. We're saying n is going to equal this repeating decimal. So we're going to use this little technique. I'm going to now take, and I'm going to multiply. Let me rewrite this. N is equal to 0.3737, etc. I'm going to take, and I'm going to multiply n by 100. 100n. If this is the value of n, and we multiply it by 100, what it does is, you should recognize this from earlier, it shifts our decimal point over 2 places. And it's going to be 37.3737, etc. 0.3737 times 100 is equal to 37.3737 repeating. I'll let you pause and just sort of make sense of that. Now what I'm going to do is I'm going to write this. 100n equals 37.3737, and n equals 0.3737. Notice that in both of these numbers that we've created, the decimal parts of them are identical. Okay? Everything from the decimal point on is the same. It's exactly the same. The decimal portion of both of these numbers is going to have point and then 37, 37 repeating. 100n has the 37 also in front of the decimal. So the little technique we're going to use here is we are going to take 100n and we are going to subtract n from it. We're going to do a little subtraction problem. When we subtract 100n minus n, we get 99n. When we take 37.37 repeating and subtract 37 repeating, what's left? Only the 37. This part gets subtracted from here and basically eliminates the 0.37 in the other number. So again, we're taking the top number minus the bottom number. And we're left with this nice, neat little algebraic equation. 99n equals 37. And if you recall from some previous algebra experience, when you're trying to solve for your variable, you're going to divide by whatever it's multiplied by. And we get n is equal to 37 over 99. And what was our goal? Our goal was to take the number 0.37 repeating and write it as a rational number in the form a over b. So 0.37 repeating is equal to the fraction 37 over 99. And this is one we can check with the calculator too. If we pull up a calculator and do 37 divided by 99, you'll see it's 0.37 repeating, and that will just go on forever and ever. So this is what we get, 37 over 99. So the first time you see that, that might be a little perplexing. We're going to try a few more of these. So let's try it with 0.57. Actually, let's do it with 0.7 repeating. We're just going to do 0.7 repeating. So if we let n equal 0.7 repeating, which is equal to 0.777, and on and on and on, we are going to take, and this time we're going to just multiply n by 10. So n is equal to 0.7777. And if I multiply it by 10, it's going to shift this decimal over one spot. So it'll be 7.777. Now, the reason I only did 10 here was because if you think about what we're going to try to do, we're going to try to subtract, right? We take 10n, which is 7.777, repeating. I should have really had those repeating dots there. And we're going to subtract n, which was 0.777, repeating. We need to, when we do this technique, find a way to get the decimal sections of the number to look identical to each other. That's what it all comes down to. Can you manipulate these through some multiplication by 10 or 100 or 1,000 to get the decimal portions identical? And all we had to do here was multiply by 10. If we subtract these, 10n minus n is 9n. 7.7 repeating minus 7 repeating is just the 7. All this stuff gets subtracted and cancels out. Divide both sides of our little equation by 9, whatever number's in front of that n, and we find out that n is equal to 7/9. So the repeating decimal, the 0.7, is equal to 7/9. Now you might be saying, JB, for the first one you did, it was 37, so 0.37, repeating, was equal to 37/99. And the next one you did was 0.7 repeating, turned out to be 7/9. Is it something, there's something to do with these nines in the denominator? Yeah, actually there is. Maybe you could guess if I put 113.113 repeating. Could you take a guess at what that might be? If you said 113/999, you'd be right. That is exactly what it is. I can prove it to you through that calculator. 113 divided by 999, 113, 113, 113, etc. So yeah, it's always going to be 9 or 99 or 999, depending on how many place values you had. If your repeating decimal started with the very first digit. So if the repeating numbers include the first digit, then that's going to work. But that's not always how it is going to play out. Okay, so let's look at some an example, a situation where it doesn't start with the repeating digit. Let's let n equal 0.57272, repeating. So how might we do this one? So the first thing you might look at is like, what would happen if we did 10n? Multiply it by 10. It's going to shift that decimal one spot over, and we get 5.7272 repeating. If we try to subtract n, in this case, we would be subtracting 0.57272. Notice how those are not the same decimals. Remember, we had to have everything in the decimal section be identical? It's not this time. So we're going to have to do something a little bit different here. I'm going to undo the things I just wrote. So we now have 10n is equal to 5.7272, etc. I've now got all of my repeating stuff at least in the decimal zone, right? The 5 that didn't repeat is out front, in front of the decimal. What I'm going to do now is I'm going to take this thing and I'm going to multiply it by 100. Why 100? Because if I multiply it by 100, it's going to shift my decimal 2 spots over here, and then I'll have another decimal that starts with that same 7.2 after the decimal point. I'll show you what I mean by that. If I take this times 100, I now have 1,000n is equal to 572.72. 7272, etc. Just wanted to delete that little line underneath, but it deleted my 7. So take a look at this. We have 10n, which is 5.72 repeating, and 1000n, which is 572.72 repeating. 1000n is equal to 572.7272 ... And 10n is equal to, make sure to line up your decimals, 5.7272 ... Again, here was the value of 10n. Here was the value of 1000n. Look at what we have in these decimal areas now. They're identical. We got them to be identical, so now we can subtract them. 1000 minus 10 is 990. N is equal to 572 minus 5 is 567. Our last step is always to divide by whatever's in front of that n, 990. And we get n equals 567 over 990. So that took a little more effort, right? That one took a little more manipulation. We still had the 99, but we also had a 0 at the end there. Okay, so this process is a bit challenging, but after a little practice, after a little work, I think you'll be okay with that. So I'm going to have you try one of these on your own. Try one of these on your own. So let's do this one. Let's let n equal 1.067, and the 67 is the repeating part. Okay, so this might take you a few minutes, but give it a shot, try it, and then unpause the video. So the first thing that we want to do is we want to find a way to get our repeating part of the decimal immediately after the decimal point. We want to shift that one spot over. So that's going to take multiplying by 10. So we will say that 10n is equal to 10.67, and the 67 is the repeating part. I'm just going to use the line. Now I need to, actually, I'm not going to use the line because I think it's helpful to see all the 67s, or at least a few more. Now I need to move the decimal so it goes to the next repeated part. It's got to like skip the repeated part. So that's going to take a multiplication by 100 because it's 2 decimal places that I need it to move. So that will give us, again, 1000n equals 1067.6767 repeated. Again, it shifted this decimal 2 spots over. We have 1000n equal to 1067.67 repeating. And we have 10n equal to 10.67 repeating. Notice how my decimal sections are lining up. They are identical. So when we subtract, we get, again, 990n equals 1057, and we divide by 990. We get n is equal to 1057 over 990. There is our fraction that equals 1.067 repeating. Let's take a look at a calculator just to double check it. What was it? 1057 divided by 990. There we go. 1.0, and then those 6 sevens just keep repeating. So if we think about, again, what we were trying to do here, we're analyzing rational numbers. Rational numbers are numbers that can be written as a fraction a over b. Terminating decimals are fairly straightforward. We just use the final place value. Repeating decimals require this additional technique.